All right, we're going to continue with logarithms, and what we're going to do is we're going to go over some rules and, I guess, techniques, different ways you can break down logarithms, combine logarithms, simplify them, evaluate them, use them to solve other problems. And we're going to start with this rule here. This is adding logarithms that have the same base. And they have to have the same base for this to work. And this rule here is very closely related to one of our exponent rules. So just quick review here. If we add x to the third multiplied by x to the fifth, what we would do to simplify that is just add the exponents together. So when we multiply similar bases with exponents, we add the exponents. So here what we have is we have similar bases. These are both base 6 logarithms. And right now we're adding them. But remember, the result of taking a logarithm is an exponent. So you can think of both of these big terms here as exponents that we're adding together. And when you add exponents together, what you're actually doing is multiplying. So the way this is going to work, to combine these logs, you're going to keep it as log base 6, but you're going to multiply the numbers. You're going to multiply the 4 and the 9. So with exponents, multiplication means add the exponents together. With logarithms, which are the inverse of exponents, addition means multiply your numbers together. So you have log base 6 of 36, and we can evaluate this. We know 6 to the second power is 36, so this is going to be a 2. So that simplifies all the way down to a nice result here. On example 2, we're going to use this same rule, the same technique to split the log. That's a nice little wordplay there, split the log. Okay, I didn't intend for that, but we're going to go with it. So what we're going to do is we're going to take log base 5 of 25, and we're going to take log base 5 of x. And because those were multiplied together, when we split them, we're going to use addition. So just the reverse of what we did on example 1. And the reason we might do something like this is because my first term now is something I can simplify. I have log base 5 of 25, and I know 5 to the second power is 25. So that simplifies to a 2. The second part of this, I can't really do anything with it, so we're just going to leave it like that. So 2 plus log base 5 of x. So let's do a couple more examples related to this here. Here we've got some fractions. And remember, fractions, when we're talking about exponents and logarithms, fractions are the result of negative exponents. So again, I'm going to start by combining these using my rule. I can multiply these numbers together. So I'm going to have log base 8 of 1/4 times 1/16. When I multiply those, I get 1 over 64. And now I want to think, okay, what power of 8 would give me 1 over 64? Well, I know 8 to the second power gets me regular 64. This is the reciprocal of that, so it's going to be 8 to the negative second power. So that's going to be a negative 2. Example 4 here, it's kind of like example 2 on the previous slide. I'm going to split this. I'm going to do log base 3 of 9. And I'm going to do log base 3 of radical 27. And those are going to be added together because I took multiplication and split it. The first part of this is pretty simple. It's going to be a 2 because 3 to the second power is 9. The second part here, I'm going to do a little more work. What I'm going to do is I'm going to rewrite this 27 as 3 to the third power because I know 27 is 3 cubed. And I'm going to do a little more work, and this is going to be kind of a tight squeeze here at the bottom, but stay with me. I know from what we learned about radicals that the square root is taking something to the 1/2 power, and we can rewrite square root of 3 to the third as 3 to the 3/2 power. All right, finally, one thing we learned about logs is when the base and the number here match. So we have log base 3 of 3, and then we have that exponent 3 to the second power. Our answer is just the exponent because the idea is 3 to what power equals 3 to the 3/2 power. And it would just be 3/2. So this would break all the way down to 2 plus 3 halves. And if you want to add those together, you will get 7 halves, or 3.5. So I know that was a lot of work, but I just want to show you that you can use this technique to break things apart. So you have one part that's really easy to deal with, and then you can focus on the part that's going to take a little more time, and then at the end you can put them back together. All right, next rule here is with subtraction, and just like with exponents, multiplication and addition go together, and division and subtraction go together. So with exponents, we would say, let's say we had x to the 9th divided by x to the 4th. What we would do there is we would subtract the exponents and we'd get x to the 5th. So we divide by subtracting the exponents. Here we're going to go the other way. When you're subtracting logarithms with the same base, you end up dividing the numbers. So log base 3 of 54 minus log base 3 of 2, we can combine that into one log that would be 54 over 2. Now 54 over 2 is going to be 27, so this is log base 3 of 27. So now we're to a point where we can say, well, 3 to what power is 27? And 3 to the 3rd power is 27. So that would be a 3 as our final answer. So very similar to what we did on the previous slides, just we're going subtraction to division or division to subtraction. So here on number 6, we're going to go the other way, and we're going to split this into 2. And we're going to say log base 4 of x. We're going to say log base 4 of 256. And here we're going to subtract them because we were dividing those. And so similar to what we did on one of the previous slides, the reason we would do something like this is because even though we can't do anything with log base 4 of x, we do have something we can do with log base 4 of 256. So log base 4 of 256, 4 to the 4th power is 256. So that's going to be equal to 4. So what you're going to get here is this first term is just kind of stuck as it is, but then you have a minus 4. That second term works out to a nice integer. So we're going to do a couple more examples of this type of problem. So here we've got log base 3 of 2 minus log base 3 of radical 36. So what I'm going to do here is I am going to divide, and I'm going to write this as log base 3 of 2 over radical 36. And, you know, why I don't know why we need to write it as radical 36, because radical 36 is just plain old 6. So there's more complicated ways to break this down, but I'm just going to rewrite that as 6. The radical doesn't really do much here. And then 2 over 6 simplifies to 1/3. So I have log base 3 of 1/3. So my final answer, I think 3 to what power, to what exponent is 1/3? And that would be to the -1 power. So you just divide them, you simplify them as much as you can, and hopefully like on that one, you get something that works nicely with whatever your base is. Here, this is one thing I want to start looking at. So we talked about this a little bit when we talked about E. So E is the natural exponential number. And when you take a log with a base of E, it's called the natural logarithm. And so the way you see that written is ln. So what ln means is it means log base E. So whenever you see ln, the base of your log is E. So here's what we're going to do. We're going to split this up. We're going to say ln of 1 minus ln of radical e to the 5th. So what we can do here, ln of 1, any log of 1 is always going to be 0, because anything to the 0 power is 1, and that's the only way you get 1 is by taking something to the 0 power. So this will be 0 minus ln of e to the fifth, that's going to be ln of e to the, we're going to rewrite that with a fraction, with a rational exponent. It's going to be 5 over 2. And then remember, this has a base of e. This is log base e of e to the 5 over 2. So it's kind of similar to one of the ones we saw earlier. You're asking yourself, what power of e gives me e to the 5 over 2? And it would just be 5 over 2. So you have 0 minus 5 over 2. And you can simplify that, and it's negative 5 over 2. So just to make sure we're clear here, because I know we've talked about this briefly, but whenever and I'll just make up something up here. You don't have to write this down if you're getting notes here. Whenever the base matches the number you're taking the logarithm of and you have an exponent, then basically what happens is this part, the log and the number cancel out, and your answer is just whatever the exponent is. So that's what happened here with ln of e to the 5 halves. The ln and the e cancel each other out, and you're just left with whatever the exponent is. All right. Next thing to look at, and this is actually what I was just talking about, but I just want to reinforce it, make sure it's clear. Well, it's similar to what I was just talking about. Whenever these two numbers match, they cancel each other out. And if we have an exponent, then that's going to be what's left. Here we don't have an exponent. So when they cancel each other out, your result, what you're left with is just 1. The idea being you've got 11 to what power equals 11. So it'll be 11 to the first power. So here we have ln of e. Well, ln is log base e. So e to what power equals e? It would be 1. So whenever the base matches the number you're taking the logarithm of, if you don't have another number in there, you don't have an exponent, your answer is always going to be 1. So that's just something I want to make sure is clear, because that will come up, and that's going to be a technique we use to cancel things out with logarithms. Whenever you can get something like this or this by itself, then you just cancel out the logarithm. You don't have to worry about it anymore. All right. Next one here is kind of continuing on this same thing, simplifying with logarithms with exponents. And what we saw is that the exponents can cancel, or if the base and the number are the same, those cancel out, and the exponent's the only thing that's left. But what if they're not the same? Like here, we've got a 5 and a 25. Here, this is a log base 10, and we have a 7. So they're not matching up. Or what if we have like a variable? We can still do things with the exponent, and here's how it's going to work. What you can do with the exponent is you can bring it out front. So log base 5 of 25 to the 9th power is always going to end up being equal to 9 times log base 5 of 25. So what you can do is you take that exponent, you move it out front, and it becomes a coefficient. And we can work this out now. Well, log base 5 of 25 is 2, so this becomes 9 times 2, which is 18. And one way you can check that if you want to is you can take 25 to the 9th power, and what you'll find is that the answer you get is 5 to the 18th power. So it'll work out. Another way to think of this, if you want to think of it this way, is 25 is 5 to the 2nd. So we could rewrite that this way. And if you simplified that, you would end up with 5 to the 18th, because you'd multiply those together. And then you could follow what we had learned earlier and said, okay, when the numbers match, the exponent ends up being your answer. So the main thing here, though, is whenever you have an exponent in your logarithm, you can pull it out front and make it your coefficient. So I'm going to erase this underneath so it doesn't get too cluttered here. And we're going to look at the next one. And then the next one, this is a good example of how we can use this to solve problems. We have log, there's no base, so it's understood to be 10. Remember, if there's no base, it's automatically 10. So log base 10 of 7 to the 2x power. So here, x is an exponent. And when x is an exponent, it's very hard to deal with because it's kind of stuck. But one way we can get x out of the exponent is by using a logarithm. And so what's going to happen here is I'm going to pull my exponent out front. So I'm going to have 2x, and then I'm going to have log 7. So I can't simplify it any further. But what this allowed me to do is bring my variable out of the logarithm. So now this is something I could start to work with or start to solve for. Last one of these on this slide here. This looks really complicated. So we have ln, which is log base e. That doesn't really matter so much here. What matters is what's in the log. It's 4th root of x minus 2. So I'm going to rewrite that. Remember, 4th root is the 1/4 power. So I'm going to write it as x minus 2 to the 1/4. And then I'm just going to do the exact same thing I've done on these other ones. I'm going to pull that 1/4 out front. It's going to become 1/4 ln and then x minus 2. And there's nothing else I can do to simplify that one. That's as far as I can go there. But that's how you can get rid of that radical, turn it into an exponent, bring the exponent out front. I know there's a lot going on here. We don't have too much left. These are the last 3 examples. And these kind of bring together various things we've looked at here. So we're going to write these as a single logarithm. So we're going to combine these. And so this first one, actually, we can write this as a single logarithm and actually simplify it all the way. So let's go ahead and do this. The first thing I'm going to do before I combine these are both log base 10 because there's no little numbers. So they're automatically 10. But I want to get rid of this 2 that's in front. I'm going to put it back into the logarithm. So I'm going to rewrite this way. So that 2 that was out front, I'm going to bring it back in and make it an exponent. So the reverse of the sort of thing we did on the previous slide. And then I'm going to simplify it. 5 squared is 25. So now I'm going to have log base 10 of 4 plus log base 10 of 25. And then I'm going to use my multiplication rule. I can combine those by multiplying the numbers. I get log of 4 times 25, which is 100. And that would be the single logarithm we're looking for. But we can simplify this because remember, it's log base 10. And the number we're working with is 100. So we're thinking 10 to what power, to what exponent is 100. So our answer here would be 2. So that one works all the way out. Next one, this one's fun. We're subtracting, so that's going to involve division. And again, I'm going to rewrite this by putting this 2 right here back into the logarithm. So I've got log of x cubed minus 8 minus log of x minus 2. And that 2 is now going to be the exponent, so x minus 2 squared. Now I'm going to rewrite this using division because I know subtracting logs is the same as dividing within the log. So these are log base 10 again because I don't have the little number. So log of x cubed minus 8 over x minus 2 squared. So that looks like I might be done, but here's something we've got. If you look at the top there, that is a difference of perfect cubes. We can factor that. So I'm going to factor this. This factors to x minus 2 because 2 is the cube root of 8. And if you remember how this works, we end up with x squared, and we get 2 positives in our second parentheses, plus 2x plus 4. And on bottom, and I forgot the word log, which is very important. Forgive me for doing that. I'll squeeze it in there. On the bottom, we have x minus 2 squared. I'm going to write that as x minus 2 times itself, because what I can do here is I can cancel out my x minus 2's. So my final answer, and I'm going to write it up here so I have a little more space, is log, and there's no little number, so it's log base 10 of x squared plus 2x plus 4 over x minus 2. So I can't really go any further than that, but I was able to simplify it quite a ways. Last one. We have a number out front that needs to be distributed. So what we're going to do is we're going to multiply this 3 by both of the terms. So we have 3 times ln of 2x minus 3 times ln of y. And now what we can do is we can take that 3 and bring it into both of those logarithms, both of those natural logarithms. So now we're going to have ln times 2x to the third power minus ln of y to the third power. Notice I put that 2x in parentheses because I want it to be really clear that the 3, the cube, applies to the 2 and the x. They both get cubed. They're both part of what is being cubed. So now I'm going to simplify this a little further. 2x cubed is going to give me 8x to the third power. And then I have minus ln of y to the third power. My final step here is I'm going to combine these into one logarithm using division. I'm going to make a fraction here. So I'm going to have ln of 8x to the third over y to the third. So lots of different little things you can do with these logarithms, a lot of little tricks, and different tricks are going to come up in different places and going to be useful for different things. So I know it covered a lot, but the assignment I'm going to give you is going to cover a lot as well. So hopefully this gets you ready for most of it. So there you go. That's a bunch of examples of logarithm rules.